Good morning. I'm Maria Paula Marques. I am a Portuguese researcher. I use neutron scattering techniques a lot in my research, and I work in the University of Coimbra in Portugal. Today, I will be talking to you about neutrons as probes for soft matter, and I will address cancer cells as well as burned bones. So vibrational spectroscopy with neutrons is complementary to the vibrational spectroscopy with the optical radiation. And of course, you can infer about structure by INS, inelastic neutron scattering, but this is complementary to FTIR and Raman. But you can also get information on dynamics by quasi-elastic neutron scattering, which is, as the name says, nearer to the elastic line. So today I will talk to you about two very different types of samples, and this goes to show the very high versatility of these techniques because they can address from simple molecules to cells, to bones, to tissues. So every type of sample is suitable to be tackled by neutron scattering methods. I will be addressing normal to cancer transition, new chemotherapy approaches, namely metallodrugs, as well as heat-induced changes in human bones. Starting with the normal to cancer transition. So most of these experiments were performed at ISIS neutron and the muon source, that is in the UK, near to Oxford. They have two target stations, and within these target stations, we used different types of spectrometers and also diffractometers and also imaging at IMAT. This allowed us to tackle, first of all, normal to cancer transition, which despite its very high importance in human health, it's still very poorly known. And we are studying it focusing on intracellular water dynamics, since any disruption of the coherent structure and dynamics of water inside of cell is likely to interfere with cellular function and also with cell growth. So there is an impact on normal to cancer transition because it affects cellular plasticity, which is known to be higher, usually higher, so changed in malignant and invasive cells. So water can also be seen as a potential new drug target, and we also studied this issue. Going from cells to a neutron scattering instrument is hardly a straightforward task. So we had to go from the cell culture lab and culture a high amount of cells because a quite high amount is needed to fill the beam. And we went to the beam, so we put the cells into the beam, and this was the first time cells were put into the beam at ISIS. And in this way, we could address intracellular water after performing isotopic substitution of all the extracellular water. So we only wanted to observe the intracellular water. And in this intracellular medium, you have two types of water at least, which is the water within the cytoplasm, the cytosol, and the highly ordered water, which is the hydration layer around each biomolecule. We addressed this by QENS, so we wanted to study the dynamics of water by QENS in cancer cells and non-cancer cells, and also in drug-treated cells. And this is just a scheme to show you how we had to fit mathematically the experimental data. So we had to fit it taking into account the various dynamic components within the sample. And these are biological samples, so quite complex ones that have different contributions, dynamically speaking. So we had to use, in our case, 3 Lorentzians, apart from a delta and a background. This allowed us to obtain a very good fit and, of course, to get quantitative data about the dynamics of each type of water inside the different types of cells. As an example, I will show you human cells, healthy versus cancer, for prostate and for breast cells. And you can clearly see that there is an increased flexibility for malignant cells, represented here in red, versus non-malignant ones. So this was something that was already inferred, but there was not really scientific data to show that this flexibility is really increased in cancer cells. Also, for different types of cancer, and this was a very quite interesting information, for different types of cancer, and here I'm comparing prostate, breast, and bone cancer, osteosarcoma, the flexibility is completely different. So all these are malignant cells, but there is an increased plasticity depending on the type of cancer. If you see, osteosarcoma is the one that is less flexible, as opposed to prostate cancer, which showed a very, very high plasticity. After addressing cells, we decided to increase the complexity of our soft matter sample, and we put tissues into the beam. So these tissues are biopsies from patients. We have an ethical agreement with an oncology institute in Coimbra, and so we got resection specimens from breast and from tongue cancer patients, and we were comparing bulk tumor versus bulk tumor-free surrounding area, what is usually called, chirurgically speaking, the frontier tissue. And we saw that there are distinct dynamical behaviors which depend on healthy versus malignant, healthy versus malignant, and also on the type of cancer. Here on the left, we are comparing tongue and breast cancer, and we can see again that the plasticity, the flexibility, the dynamics are different. Of course, after fitting, we can get quantitative data. This data is for tongue normal tissue and tongue cancer tissue, and we can get data for the two types of water, for the cytoplasmic water and for the intracellular and hydration water, which of course is more rigid, as you can see in this Y scale. And we can get, according to a jump diffusion model, which is the one that best fits our data, you can get values for the residence times and for the diffusion constants. So you can get quantitative data comparing cancer and non-cancer for the different types of water inside a cell. So understanding better how intracellular water dynamics works for a normal to cancer transition, understanding this at a molecular level, which had never been tackled before with neutron scattering techniques, we can aim to get an early cancer diagnosis and, of course, to discriminate better tumor-free surgical margins. And, of course, we can attain improved chemotherapeutic approaches where water can be seen as a new drug target. This takes me to the drug impact on intracellular water, taking water as a target in human cells. Here you can see that when you compare drug-free in black to drug-incubated in color cells, this was done for triple-negative breast cancer cells, human cancer cells. You can see that there is a very clear mobility reduction within the intracellular medium as a function of drug and for increased concentrations of drug. So the drug is affecting the cytoplasm. And the drug affects differently cytoplasmic water and hydration water, which was a very interesting finding for us. Regarding cytoplasmic water, you can see that the drug prompts an increase in organization. So the cytoplasmic water has a restricted mobility. In turn, as opposed to cytoplasmic water, the hydration layer is completely disrupted by the drug, and so the drug induces a higher mobility of this previously highly organized layer. This was a very interesting finding for us to know that the drug not only affects water inside the cell, but it impacts on it differently depending on the type of water. Again, we studied for DNA, for instance, not cells, but just DNA, which was extracted from cancer cells. And we, again, performed isotopic labeling. So we have profiles of elastic intensity versus temperature for D2O DNA or H2O DNA. And you can see that there are distinct effects for different agents. And here we are comparing palladium agents in blue with platinum agents similar to cisplatin, a clinically used drug, which is here represented in red. The same concentration for both of them. And you can see that they behave differently. While cisplatin and platinum-based agents affect more DNA's spine of hydration, enhancing its plasticity, the palladium compounds affect DNA's backbone and also increase its mobility. This study was done at NIST, so in the United States, because we needed to address not only a picosecond, but also a nanosecond timescale. So we needed a different instrument from those available at ISIS. So to sum up, there are distinct effects for platinum or palladium compounds. The impact varies with the type of cancer. So we saw selectivity. So I couldn't show all the data here for time's sake, but there is a different effect on breast cancer cells, on osteosarcoma, on lung cells, depending on the type of agent. And this tells us that there are different modes of action for cisplatin versus polynuclear agents with more than one metal center, and different modes of action for platinum versus palladium agents. In a nutshell, cisplatin affects more DNA, proteins, and membrane lipids, while a compound with not one but two platinum centers affects more the lipids, mostly membrane ones, and its analog, where we substituted platinum for palladium, impacts more on DNA backbone, as we saw previously, and on proteins. So there are definitely different targets and different modes of action and selectivity regarding the type of cancer. Going to the final subject of this small talk, this short talk, we also tackled with the Newton scattering techniques human bones and how they are affected by heating. This is a very important matter, forensically speaking, because burning events are known to affect the crystallinity and microscopically the bone. And also these changes in crystallinity affect the microscopic properties like color and dimensions of the bone. The bone changes color, it is wrapped, sometimes it is fractured, so everything changes, which means that osteometrics, so the tables that are available to forensic scientists in order to identify a victim or a body, a skeleton, are not applicable anymore. So these osteometric tables were made for unburned bones. Since there are so many heat-induced changes on bones, no identification is possible. This is a very serious matter, sociologically speaking, because when you have an accident, a crash, a terrorist attack, a plane accident, you cannot, and the only thing you find are burned skeletal remains from the victims. These victims remain unidentified. Just for you to have an idea, from the 9/11 terrorist attack, there are still 1/3 of the victims, almost 1,000 victims, are still unidentified. And this is a very serious problem. So our study aimed to relate burned to pre-burned parameters in order to be able to then use the osteometric tables available for forensics. So we studied by burning under controlled laboratory conditions modern human bones. So we cut them and we burned them under controlled conditions, either aerobic or anaerobically, at specific temperatures. We were lucky enough to have a skeleton collection in the University of Coimbra. We have, in fact, two, one with identified skeletons and the other one of unidentified skeletons, and half of each skeleton is available for science. This is a unique collection in Europe, by the way. So we started by studying these modern human bones, and then we went to forensic and archaeological skeletal remains. So we went to real cases. This collection is hosted at the Laboratory of Forensic Anthropology at the University of Coimbra. And the burnings were made in a special oven. The temperatures went from 200 to almost 100 and 1200 Celsius. We did combustion, this means aerobic, but we also did, after all, anaerobic conditions. And the bones looked like this when you inserted them in the oven, and they changed like this, so drastically after being severely burned. Sometimes, so for you to compare an intact femur with a femur burnt at moderate temperatures or at high temperatures. Sometimes, very often, they even break. So they wrap, they break, their dimensions and their color changes. So this is a multidisciplinary study where we use inelastic neutron scattering to understand which were the spectral biomarkers, to assign all of the bands from hydroxyapatite as well as from the organic components in bone, which are proteins, mostly collagen and lipids. We also did neutron diffraction to focus on the H's, optical vibrational techniques also to get spectroscopic ratios and spectral biomarkers, and X-ray diffraction to focus on the heavy atoms, so for structure. This multidisciplinary study allowed us to attain a quantitative understanding of the heat-induced changes in human bone. And just for you to have a couple of examples, for instance, INS at MAPS, and MAPS has a high sensitivity for high frequencies, allowed us to detect the destruction of the organic constituents of bone and variations in the bioapatite's microcrystallinity. So if you compare unburned bone, so all of the bioapatite OH bands were for the first time assigned. And in the unburned bone, you still have protein and lipids. Also, if you burn the bone at moderate temperatures, there are still traces of the organic components. But if you increase the temperature of burning, there is almost no proteins nor lipids. And for high temperatures, there are no traces at all of organic constituents, and the spectra almost superimposes hydroxyapatites. Also, if you go to another instrument, Tosca, which has a very high sensitivity at low wave numbers, you can probe the low frequency modes of bone, which reflect its crystallinity changes according to temperature. So we were able to detect all the lattice modes and low frequency bands, and these were changed as temperature increased. And it was a very interesting finding that there was a calcium hydroxide stretching that was only observed above 700. So this is a scientific proof of definite changes and very serious changes in the crystallinity of the bone as a function of temperature. So we could attain the first quantitative relationships, and interestingly enough, these were not exactly the same for different types of bones, and here we are comparing femur and humerus, and we could detect some biomarkers, for instance, the librational band of the OH or the stretching band of the OH, and also a stretching of the phosphates. These were biomarkers because their variation with heat was consistent and was very defined, so they can be used as biomarkers. In this way, we could finally, and this paper came out in 2020, unburn the bone, and we could detect to which extent the bone, to which extent the dimensions of the bone were affected by heat for different types of temperature. For instance, here, the slide shows that at 1000 Celsius, there was a decrease in the dimensions of 10%. So we could unburn the bone and allow the forensic scientists to use the osteometric tables that are available for unburned bones. So the effective heating conditions was performed for aerobic, so combustion, but then we went also for anaerobic burning because in some cases of accidents, the bones are burnt under not totally aerobic conditions, but with deprived oxygen. So if you see the appearance of the bone is completely different when it is burned with oxygen or without oxygen. And if you compare the spectroscopy, the spectra performed at MAPS and Tosca for unburnt, burnt aerobically in blue and anaerobically in violet, you can see that there are very defined changes. So, in simple words, the organic components are destroyed at higher temperatures under anaerobic conditions. At the same temperature, aerobically, you see no traces of proteins or lipids, whilst under anaerobic conditions, you can still see them. Here we decided to do neutron diffraction, and we did this measuring at GEM to determine heat-induced crystallinity changes under aerobic versus anaerobic burning. And our bone was inside, the bone samples were inside these sample holders, which were put inside an oven under vacuum, and this was inserted into the beam. And under aerobic conditions, we got these diffraction patterns, whilst under anaerobic ones, we got the diffractions that you see on the right, from room temperature to 1000 Celsius. And you can clearly see that whilst under aerobic conditions, the major changes occur below 800, for anaerobic heating, the opposite occurs and the major changes take place above 800. So the burning conditions have distinct effects on bone structure and crystallinity. That means that from these differences, we can also infer on the conditions of burning. At IMAT, we did a very preliminary study, from which I'm only showing you this slide, and you can see that the amount of organic content is much, much higher at lower temperatures, as expected, than at higher temperatures. So from the modern bones, we went to real cases, and we were approached by archaeologists who wanted us to study several archaeological remains, bone remains, that they thought had been cremated, but they wanted to infer more about the conditions of burning. So we were given several skeletal remains. Of course, these samples cannot be damaged at all, so they were put into the beam as it's shown in this image. And we can get all kinds of information on funerary practices, on types of fire, on availability of oxygen, for instance, on individual biological profiles, on the storage conditions, on the type of environment, because we can also see some signals in the spectra from types of soil, from, for instance, if a coffin was used, if the skeleton was wrapped in a tissue, if there were some remains of oils or pigments, for instance. So all these informations are important to infer on practices of ancient civilizations. And just to finish, I would like to show you one of the most interesting results we obtained for a skeleton from the Roman period of the Guidonia archaeological site near to Rome. This was said that, so the three remains that we were given, 1, 2, and 3 different types of bones, the archaeologists told us that they were definitely from one skeleton, the same skeleton. But when we ran the spectra, in this spectra are INS spectra measured in Tosca, we saw clearly by comparing with references, so modern bones that we had studied before, burnt at controlled temperatures, we clearly saw that the femur, 3 in blue, was burned to a different temperature, a lower temperature than the humerus in red, and this again to a quite lower temperature than the fibula. So apparently we had 3 different fragments from the same skeleton, and one of them was burnt at 400 degrees, the other around 600, while the last one around 800. This was quite puzzling for us, so when talking to the archaeologists, they were very, very happy, because they saw this was the first experimental proof of a practice they thought was followed in this period. And this practice was to bury the dead people not without a coffin, so just in the soil, so in a fetal position, and after burying it, these skeletons, these bodies were burned inside the grave. If this particular body was burned from right to left, this would very easily explain the different temperatures we measure spectroscopically, higher for sample 1, then lower for sample 2, and even lower for sample 3. So this was really an interesting result. Also, we saw some contamination from the limestone soil where the skeleton was found. Some contamination was seen here. And this was a very interesting result that shows how useful these techniques can be, mainly Newton scattering techniques, since bone has a high amount of hydrogen, so it is very sensitive to neutrons. This came out, surprisingly enough, in Los Angeles Times, and we presently have more work in progress regarding bones. One of them is the characterization of metastatic lesions in human bone. Apparently, when we have metastatic lesions that are shown here in yellow, there is a different amount of organics, but these are still preliminary studies. And lately, we have been approached by the curators of the National Museum of Brazil, which suffered a very severe fire in 2018. And from the Egyptian mummies that the collection contained, they now only have skeleton burned remains. So we are studying this also at Tosca. Here you can see some INS data and maps in order to determine the conditions of burning, the temperatures of burning, aiming at better preserving these remains. And with this, I would like to thank you for your kind attention, and all queries are welcome, probably by writing. Thank you.